degeneration of mirror symmetry for Lattice. Okay, so back in this paper, we talk about this, we give some general things, we talk about the toric case in various places. And since that paper came out, Atsushi Kanazawa has actually proved the sort of rigorous version of this statement in the elliptic curve case, and even more recently in stuff that hasn't appeared yet. He's also proved it for, in general, high-dimensional complex tori. So, the real question is, well, okay, what happens in other cases, right? So the first non-trivial case, which I'm going to sort of look at for today, is what does this say in 2 dimensions? I.e., can we say something interesting about Landau-Woodward models for finite surfaces? Using mirror symmetry for lattice polarized K-freaks. Okay, so this is kind of the first non-trivial case that's not already been sort of fully dealt with. And let's talk a little bit about Fano surfaces. I should probably, I've left a convenient gap here, I should probably say weak Fano surfaces. Fano surfaces are just Del Pezzo surfaces, there aren't very many of them. If I allow weak, then I get a few more. Oh, this one doesn't work very well. Maybe I'll ignore this one. Did anyone actually read that? Yeah. Because that's not bad. It looks worse when you stand closer to it. A weak Del Pezzo is a smooth, rational surface X with, so a regular Del Pezzo surface has ample anticanonical divisor. I'm going to assume that the anticanonical divisor is just Neff and big, which gives me a slightly larger. And I'm going to make a choice of the anticanonical divisor, E in the linear system minus Kx, and D, which is K of x squared, is a degree. And it's well known that D is somewhere between 1 and 9, but there are 2 cases when D is equal to 8. This is all very classical stuff. Now I go for the long walk to the other end. Okay, so obviously mirror symmetry for these things has been studied before. In particular, it's been studied by Oru, Kapsakov, and Orlov in a paper from 2006. What do they say? They say the mirror to a weak Del Pezzo of degree D is an LG model. What's an LG model in this case? It's a map, or I think of it as a map, from Y to the affine line, which is an elliptic vibration. So it's an elliptic vibration, and what's more, it's an elliptic vibration with 9 minus D, 12 minus D. It has 12 minus D singular fibers. and they have Kodaira type I1. So, if you don't remember the Kodaira classification, this is just the simplest type. We're just talking about nodal rational curves. Okay. An important feature of this is that you can compactify it. So it compactifies to a rational elliptic surface.
I don't think we say quite that.
Sorry?
So they don't need to be 12 minus 5%. Because multiplication doesn't affect the Foucault side of categories. So it will give fibers which give several singularities. So
Yes, this is going to come up. This is sort of generically. It's up to deformation, this is true. Up to deformation, this is true. So it compactifies to a rational elliptic surface with fibers of types. Well, I've got I1, I've got actually 12 minus d of those. And then at infinity, I have a fiber of type ID, which gives my rational elliptic surface. Okay. Okay, so the general idea is to try and add some idea is to refine this picture using lattice polarizations. Okay. Oh, that's going to happen more than once. Okay, so that's the general setup. Let's start getting in, let's start digging into the meat. Okay, so what am I going to do? Well, I need to define some lattice polarizations. We think about how these are defined for K3 surfaces. How do we define these for K3 surfaces? What we do is we define some kind of sublattice of a certain rank of the K3 lattice, and then we specify there has to be an embedding of that into the Picard lattice of our K3 surface. So I'm going to try and follow the same kind of thing. Now, of course, these, they're Pezzo surfaces. We think of these as being like log K3 surfaces. So really, we want to consider the anticanonical divisor to be some kind of boundary divisor. So if we're looking at the structure of these things, we really want to be looking at the structure of the Picard lattice, which is orthogonal to the anticanonical divisor. So I'm going to let lambda d denote the lattice E perp. So I've got this class, anticanonical class E, in pic X. So importantly, what do I know about it? It's negative definite. It has rank 9 minus D. And what's more, it doesn't depend upon the choice of the surface X or the divisor E. It only depends upon the degree D. Up to there are two cases where D equals A. It only depends on D. And you can write down what these lattices are in each case. And then with this, we can make a definition. Okay. So let's pick a primitive sublattice, L, I've got a primitive sublattice living inside this, then an L polarization on my pair consisting of X along with a choice of divisor E is a primitive embedding. So I'm just following the definition for the K3 surfaces. It's a primitive embedding of L into the orthogonal complement of E sitting inside the Picard lattice of X. But this doesn't actually give any restriction on X and E. Because the point is that E perp is always exactly the same thing. So just specifying I have some embedding going into here doesn't actually restrict my surfaces whatsoever. So what I'm going to have to do is I have to add an additional condition. This extra condition is completely vacuous in the K3 case. Such that for any root alpha in my lattice L, so for any root alpha in L, either alpha or minus alpha is effective. For K3 surfaces, this is automatic. Any root that I have in my, any -2 class I have in my K3, in my Picard lattice for a K3 surface is automatically going to be either it or its negative is effective. But in this situation, that's not necessarily true. But specifying this is effectively saying I'm forcing my surface X to contain some configuration of -2 curves which are disjoint from the boundary. And that's making it, that's then a non-trivial restriction on the surfaces that I can have.
So I don't quite understand the definition. So it seemed like you first fixed L inside of lambda D,
Yes.
but then you also consider primitive embeddings. That primitive embedding can be different than the original fixed one?
Yeah, well the point is, so lambda D is completely, so this as an abstractly as a lattice is completely independent of the choice of X and E.
So you're fixing an identification, basically.
Yeah, so I'm saying, I'm fixing an identification between this lambda D considered as a lattice, sublattice of that, and this particular sublattice. So yeah. Okay. Okay, so what do I want to do? What I want to do is I want to, follow this philosophy that I said at the start. And the philosophy was saying, well, okay, I want to consider this as a degeneration of K3 surfaces. So what I'm going to do here is I'm going to construct a degeneration of K3 surfaces where this sort of sits somewhere in the middle of it, and then we're going to try and see what that says about potential mirrors for this thing. Okay, so okay, so let's talk about degenerations of lattice polarized K3s. So what am I going to have? I'm going to have V to delta. Delta is just some sort of small analytic complex disk. This is a degeneration of K3 surfaces. Let's put it in brackets. M polarized for some lattice M. Now I'm sweeping a lot under the carpet here. What am I sweeping under the carpet? The thing I'm sweeping under the carpet is that you have to be, the definition of this is quite delicate, because you need the degeneration to respect the lattice polarization. So effectively, I mean, this is, I'm not going to make it rigorous here because I don't really have enough time, but the general idea is you force M to have certain properties of invariance on the monodromy around the central fiber in here, which means, I mean, in effect, the thing we're going to use is that it forces M to embed into the limiting mixed point structure. So we're saying, well, okay, you know, we're going to define this thing to be such that M extends onto the limiting mixed point structure. That's what I'm meaning by degeneration. An M-polarized degeneration rather than an M-polarized K3 surface. So I'm going to call this thing a Turing degeneration.
Is there some compatibility with the wave filtration?
Is there, sorry?
Or with the unipolar part of the monodromy? I mean, you say it embeds into limiting mixed point structure, but just as a lattice? I mean, is it somehow compatible with the filtration?
So you'll see in a second, I'm going to start breaking out some point structures, but it's, yeah, I mean, effectively, the weight filtration is completely forced by the form of the degeneration I'm taking. So we know in that situation that it has to be, yeah, I mean that's going to be forced by the form of the degeneration basically. It's going to, so this is a Turing degeneration if it has a form. Picture of it. It's going to consist of two surfaces. Two surfaces I'll call x1 and x2. There's a curve here which I call E12. This is elliptic and smooth. And both x1 and x2 are rational. So this is fairly, this is about as simple an example of a type 2 degeneration of K3 surfaces as you can think of. There's a lot of examples of this kind of thing. But this is just to make everything a bit easier. The same thing really works if you look at completely general type 2 degenerations. You just have to do a lot more work. So I'm restricting to the simpler case here because that's actually sufficient to state what I want. It works more generally for type 2. Okay, so here we go. Here's the mixed constructor stuff. So
this is not the maximal unipolar.
no, this is specifically not the maximal unipolar monodromy point. So the whole kind of aim of this philosophy is to try and, or part of the aim of this philosophy is to try and discuss mirror symmetry for degenerate surfaces which are not maximally unipolar. Okay, so what do I have? Well, I've got the Clement-Schmidt exact sequence. What's that going to give me? So I've got the, let's get it right, the second weight-graded piece of the limiting mixed Hodge structure. You can show that goes to 0 over here. There's the second weight-graded piece of H2 of the central fibre. Now, the definition that I swept under the carpet, which sort of answers Chris's question, is that M admits an embedding into there. Okay, what's more, this thing, you can sit down and figure out how this works. This admits an embedding into H equal to x1q, direct sum H2 x2q. I should have called this thing, I should have given one of these things a name. Let's call this map I. It's not an embedding, so I'm not sure why I called it that, but anyway. Okay, so here is the theorem, or here is a theorem. For any Turing degeneration, if one of the surfaces, let's say x1, if x1 E12 is weak del Pezzo, then what I'm going to do, M embeds into here. I can pull it back by I can embed it up here, and then I can restrict to the first piece. So what I'm going to do is I'm going to pull back M. I'm going to consider that as something in x1, but I'm going to intersect it with the integral path of x1. Okay. This is a lattice polarization. On x1, e1, 2, in the sense of the definition that I put here.
And an M polarization, I mean, is it injected?
No, it's not an M polarization in general.
So some
So effectively, it's going to be some sublattice in it. Because we're going to, effectively, this is going to, you can, so, this is stated much more carefully in the paper. But effectively, what you can show is you can show that, the lattice that you get for this lattice polarization actually embeds into M as a sublattice. But in general, so I mean, sort of the way to intuitively think about it is, you know, your lattice polarization on M, that's on some general fiber, that's specifying some big pile of curves or classes on there. You sort of take all these classes in, some of them are going to go onto x1, some of them are going to go onto x2. You just say, we're just going to restrict to those ones which are living on x1 and which are orthogonal to this elliptic curve. And that gives you precisely this. That's sort of intuitively what this is doing. The interesting bit is conversely, if xe is any L polarized weak del Pezzo, of degree D, then there exists a Turing degeneration as above, such that the following three conditions hold. Firstly, xe is one of the components of the Turing degeneration. It would be kind of rubbish if that wasn't true. Secondly, the lattice polarization. So what I do is I build a family of K3 surfaces and I put a lattice polarization on there. The lattice polarization, if I do this intersection, that just gives me exactly the lattice L back. And what's more, here's the important one, which isn't necessarily true in general. If I take the orthogonal complement of M, where does the orthogonal complement of M live? I'm talking about the orthogonal complement of M inside the K3 lattice. But then what I need to do is I take it inside the K3 lattice and restrict it to this graded piece. If I take this orthogonal complement and I intersect that with H2 of xz, then that moreover gives me the orthogonal complement of L, where that orthogonal complement is taken inside the lattice lambda D. So this last condition is one which, in order to make the next step sensible, you need to sort of have this, because for doing the mirror symmetry for K3 surfaces, we need to take the orthogonal complement of M. Right? If we're taking the orthogonal complement of M, we need that to somehow be compatible with the lattices living in here.
So what parameterizes this during the generation? Some kind of web of pairs, or what parameterizes this degeneration?
What parameter? I mean, I haven't really studied the moduli of these terribly closely. There are some statements which are sort of written down but not carefully proved anywhere. That you can. So the weak del Pezzo surfaces. I mean, we're not just looking at weak del Pezzo surfaces. We're looking at weak del Pezzo pairs. The moduli of those is moderately well understood. For the type 2 degeneration. for the Turing degenerations, these are examples of type 2 degenerations of K3 surfaces, and that's in general a fairly hard problem. Actually, like completely coming up with, I mean, that's something else we're trying to work on in a completely unrelated project, but so far, doing type 3s has been very tricky, and type 2s is currently beyond our technology. But I've got some understanding of what the moduli spaces for the Weak-Del-Pezzo surfaces, well, the Weak-Del-Pezzo pairs look like.
What's the dimension?
So the dimension of the moduli space for a Weak-Del-Pezzo pair is, it's going to be, so it's 1 for P2, and it's 2 for...
But is it coarse or the...
I think it's coarse.
But after you fix the lattice.
Oh, okay. If we're talking about lattice polarizations, yeah. So there is there should be a coarse moduli space. I've got a conjecture for what it is. The dimension once you fix the lattice is anyway. So it's you take the moduli space for the Weak-Del-Pezzo pair, which is something like 10 minus d, I think the dimension of that is. And then you just subtract the rank of the lattice.
So, is 1, is it to see regardless of
Which,
yeah.
this condition, so yeah, we could, I mean, this is much more general, right? So we could, it's quite easy to build a Turing degeneration where you've got one of the components is a given Weak-Del-Pezzo surface. The difficult part is arranging the rest.
Can you make some comment on why it's easy?
Effectively, what you have to do is, you know, you could just use these results. So there's these old results of Friedman about smoothings of degenerate K3 surfaces. So effectively, you take your component and you say, well, you know, he's got some conditions on when is a degenerate K3 surface smoothable. And so all you have to do is you just say, well, okay, I just have to come up with another surface that I can glue to this, so that if I do that, the overall thing satisfies that set of conditions. And that's fairly straightforward to do.
So what's the other surface? What's x2?
That depends very much on what x1 is. I think you can generally construct it as you take a ruled surface over an elliptic curve, but then you have to do some blow-ups to make the intersection number of the elliptic curve correct, so that it glues correctly to this. Okay, so where are we now? So this has been a lot of sort of machinery. Let's try and switch over to talk about some mirror symmetry. So let's let XE be an L-polarized Weak-Del-Pezzo of degree D, and this is a Turing degeneration which satisfies this theorem. So all of these conditions that I put on this last board hold for this particular Turing degeneration, and I should say that it's polarized by a lattice which I'll call M, keep the notation consistent. Okay, so I can do mirror symmetry for the M-polarized K3 surfaces. So let's let M sub M. This is the moduli space of M-polarized K3s. And this is, so M sub M bar is its Bailey-Baroque application. Okay, so as we said before, this degeneration is not maximally, the Turing degeneration is not maximally unipotent. So the degeneration V happens along a one-dimensional boundary component in this Bailey-Bromley application. However, I should say importantly that this boundary component in the Bailey-Bromley classification does not in any real sense provide moduli for such degenerate families. So these Turing degenerations live in much, much larger families. If we think about this, the boundary component here, it's one-dimensional. What's that one dimension? The one dimension is just precisely the J invariant of the elliptic curve that these two surfaces are glued along. But all other geometric data about this degeneration is completely lost. So this is, I mean, you know, the moduli space of such Turing degeneration commits a contraction space, and the contraction is just take the J invariant in the middle of the elliptic curve. But there's a lot of information lost here, but all we need, lattice theoretically, this is all we need. So in order to do K3 mirror symmetry, what I'm going to do, I'm going to suppose this component contains a maximum unipotent one-dimensional.
Could you recover that moduli dependence when you consider certain stable bundles on the elliptic curve?
I'm not sure about that. I mean, like, I've sort of studied this for a while, but in general it seems that the moduli space for the type 2 degeneration should just be the blow up of MM bar along this one-dimensional boundary curve. So it should have codimension 1 in the moduli space. And there's a lot of strong evidence for that, but nobody's actually been able to get anywhere close to proving it. Okay. So the reason I've used the Bailey-Bromley compactification is because the Bailey-Bromley compactification is a completely lattice theoretic object. All the boundary components are defined just in terms of lattices. So lattice theoretically, what does this one-dimensional boundary component correspond to? What does it say? It says we have a rank 1 isotropic sublattice. Not yet. We have a rank 2 isotropic sublattice I, which sits in the orthogonal complement of M. Along with a distinguished, so this rank 2 isotropic sublattice corresponds to the one-dimensional boundary component. I want there to be a maximum unipotent monetary point in there. What does the maximum unipotent monetary point correspond to? It corresponds to a distinguished primitive isotropic sublet. Primitive isotropic vector E sitting inside I. So I've got both a rank 2 isotropic sublattice and a distinguished primitive isotropic vector living inside it. Okay. Now, mirror symmetry, what does this say? So, the mirror to a general fiber in V if I'm talking lattice polarized mirror symmetry, the general fiber is polarized by the lattice M. So this is an M check polarized K3 surface. Dot W. And I should tell you what M check is. M check, I take the orthogonal complement of the vector E inside the orthogonal complement of M. And once I've done that, this still contains E. It still contains E because E is isotropic, so I want to kill E. Okay, so lemma. So what have I got? I've got this rank 2 isotopic sublattice, inside I've got a primitive isotopic vector. The idea is when I quotient this isotopic sublattice by that primitive isotopic vector, I'm left with a one-dimensional isotopic sublattice. So the lemma is that I determines a class F in the mirror lattice M check, which is isotopic, with F squared equals 0. Thus, the mirror W admits an elliptic fibration. This might not necessarily have a section. W admits an elliptic fibration over P. Okay. Moreover, there's an embedding. This requires a little bit of work to show, but it's not too bad. If I take the orthogonal complement of the lattice L inside the lattice lambda D, this embeds into the orthogonal complement of the vector F in the lattice M check, but I want to make sure that does not contain F, so I'm going to quotient out by Z of F. So let's sort of recap what's happened here. So my mirror K3 surface, W admits an elliptic fibration, and what's more, the class determining that elliptic fibration, the class F, if I look at the orthogonal complement of that class inside the mirror lattice M check, then my lattice L perp, or the orthogonal complement of L inside the lattice lambda D, admits an embedding into there. So I can think of this lattice L perp as determining a collection of singular fibers living inside this K3 fibration. Moreover, I should keep going with this, and if alpha is any root in L, or the orthogonal complement of L, then this last bit is quite easy. This is just K3 theory. Either alpha or minus alpha is effective in the Picard lattice of W. Okay. So going back to our philosophy, the philosophy says that the mirror to XE should appear. So this is what I mean by mirror symmetry for Landau. Mirror symmetry for Farnos is a degeneration of mirror symmetry for Calabi-Yau's. So XE is part of my degeneration of my family of K3 surfaces V. So my mirror to XE should appear somewhere inside the mirror over here. So the mirror to XE should appear as the restriction of this vibration to some open set. And moreover, if we want to agree with the work that's been done before, it should admit a compactification
So this W is a K3?
Yes, W is a K3 surface. It's a K3 surface which has got, well, it's really it's got a family of elliptic curves living on it. When I say elliptic vibration, I'm not assuming that there's a section, that they are. It is swept out by a family of K3 of elliptic curves which are disjoint to one another.
But in the work that you mentioned before, the Landau network, which is miracle, the Pezzo is a rational set.
Yes, so the idea is this bit is a bit tricky, but the point is, so what should happen here is what we should be able to do is we should be able to take this P1, and I mean this is sort of purely topological or being done sort of analytically. You can't do this algebraically. We take this P1, you split it into a top half and a bottom half. And over each piece, this looks like a vibration over some sort of complex disk, and we sort of just blow that out by, or we compactify it by adding a single fiber infinity, and this gives you the right thing. So this part of the construction is absolutely purely analytically. It doesn't work in an algebraic sense because this is not just got by removing one point from P1. It's got by removing some sort of analytic open set from P1 that leaves you another analytic open set. You should get a compactification by adding, I should say, to a rational elliptic surface. Adding a singular fiber of type ID. Okay. So in light of all of this, I'm going to make a mirror definition to the definition that I made before. So it's sort of, we've got a lot of the information we need now, right? We've got this lattice embeds into here. It's orthogonal to a general fiber, so it's specifying some sort of structure on the fibers. So what I want to do is I want to sort of take this and chop out all of the stuff which is not hit by L, and that should be the picture that I want here. So here's a definition. Let Y be a rational elliptic surface. And I'm going to suppose that Y contains an ID singular fiber. Let's give these a name. I'm going to call this a rational elliptic surface. Of type D. I'm going to let lambda D prime denote the orthogonal. Oh, I should probably, let's call this ID singular fiber capital D. So lambda D prime is going to denote the orthogonal complement of D. What do I mean by this? I don't just mean the orthogonal complement of the fiber D, I mean the orthogonal complement of the sublattice generated by D. Capital D has lowercase d components in it, so that generates a sublattice of rank lowercase d, yes, lowercase d living in here. So this is that sublattice. This is not just the singular fiber. In pick Y, what do I know? This one is indefinite. The sign is 1D. But importantly, as before, it only depends upon my lowercase d. It doesn't have any dependence upon the particular choice of elliptic surface in the rational elliptic surface inside the moduli space. It depends only on d. I'm going to let L check. Sitting inside lambda d prime, be a negative definite primitive sublattice. Then an L check polarization on YD is exactly as I defined before, is a primitive embedding of L check into D perp. L check into D perp, sitting inside pick Y. And I want the final condition such that for any root alpha, either alpha or minus alpha is effective. And moreover, I should note, I should have noted this a couple of minutes ago, but I forgot, I should note that this lattice lambda prime d, for any d, contains the lattice lambda d. So, lambda d sits inside lambda prime d for any d. Okay, now you might ask, this embedding is not uniquely determined. It seems that the choice of this embedding seems to be equivalent to the choice of the maximally unipotent monodromy point. When you're looking at the K3 surfaces, the choice of your maximally unipotent monodromy point automatically determines this embedding uniquely. So it seems that this choice of possible embedding here corresponds to a choice of which maximally unipotent monodromy point we'll go over to. Okay, so here is the conjecture. Let XC be an L polarized weak del Pezzo of degree D. Let L check be the orthogonal complement of L inside the lattice lambda D. Then the mirror to XC. Oh, why have I said C? I should have said E, right? Let's keep the notation consistent. Then the mirror to XE is the open set. If I take Y and remove D, in an L check polarized rational elliptic surface of track D. Okay. So, following on to that, I mean, so this is heavily suggested by the K3 surface stuff, but to make that formal, and the first part of this one is already completely proved. The difficult part is, well, I'll state it first. In the construction above, set. As I said, this can't be done algebraically. In W, isomorphic, the open set Y and SD in an L-check polarized rational elliptic surface. So, at this point, the difficult part is, so we can show, and it follows largely from what's been done above, that if I've got my vibration W over P1, the singular fibers of W over P1 is the correct set of singular fibers. So I know there's some set of singular fibers. The difficult part is showing, okay, there exists some nice curve living inside P1, which if I cut along that curve, then it sort of takes out an open set, which is isomorphic to the complex numbers, analytically, where all of those fibers appear appropriately to actually be this. So that's the difficult, tricky bit. The actual part of showing that this contains the correct set of singular fibers to actually look like one of these things is completely done and follows from what I've already said. Okay, so I'll finish off with a quick sort of illustrative example so those people who have gone to sleep or got very lost can kind of see what this is suggesting. So let's consider one of the 2 degree 8 cases. So I can look at the case of either P1 cross P1, or there's a degeneration of this to the quadric cone. So in this case, what am I looking at? So this is a del Pezzo surface of degree 8. We could say, okay, what's the canonical divisor? The canonical class in here is 2 times a section plus 2 times a fiber. We can look at the orthogonal complement of this. What's the orthogonal complement? It's just a root lattice of type A1. Okay, so I've got a root lattice of type A1. What are my possibilities for L? My possibilities for L, well, I've only got 2 possible sublattices of this. It's one-dimensional, I might have a trivial thing. So, if L is 0, what does that say? That says I'm not specifying that there are any negative classes living on my surface. So if L is 0, I'm in the P1 cross P1 case. I'm not actually specifying anything. So I have X is P1 cross P1, at least generically. The other option is L is the entirety of A1. If I'm working in A1, I've got a -2 class. So I'm saying my rational elliptic surface has to have, well, it should be F2, it should be F2. Thompson surface. If L is A1, I'm forcing there to be a -2 curve in there. So that's putting me in this situation. So in this situation, I've got F2. Okay. Now let's see what we're saying about the mirrors. If L equals 0, what have I got? I know that L check is A1. So that tells me that Y is a rational elliptic surface. With the following fiber type, well, I need a fiber of I need an I8 fiber because I'm in degree 8. What's more, the A1 here is forcing me to have an I1 fibre, an A1 fibre which is an I2, and then I make up the difference with two I1s. And if L is A1, then L check is just a trivial. So that says that Y is a rational elliptic surface. With fibres I8, I1, 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 I1. Okay. One can do this in other cases, right? So this is kind of interesting because there's a complete classification of singular fibre types of rational elliptic surfaces. So you can sit down and you can look at this and you can notice that, you know, the highest IN type singular fibre that occurs is I9. So that's a good sign to start with. The next thing you look at is you say, well, okay, if I'm looking at ones with I8 singular fibres, well, there's two distinct rational elliptic surfaces which have fibre type I8 times 4 I1. That's also a good sign. There are two of degree 8. Moreover, in one case we have a degeneration which goes to I8, I2, I1, I1. The other case doesn't admit a degeneration where all the fibre types are type I. It goes I8, 2, I1, I1. That corresponds to the fact that P1 plus P1 admits a degeneration to F2, which has a -2 curve. But if I look at the other del Pezzo surface of degree 8, which is F1, it does not have any degenerations which contain -2 curves. So in particular, the two rational elliptic surfaces of type I8, I1, 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 one of them admits a degeneration to this. This is the P1 plus P1 case. The other one doesn't admit degenerations. That's the F1 case. And you can keep going on this. You can look at rational elliptic surfaces with an I7 singular fibre, and you can see that they just correspond completely. So, okay. That's my hour, so I'll call it a day.
Alright, let's take question.
Stunned into submission.
So, you mentioned that you get some parallel work on this modular spaces.
Oh, type 2 degenerations of K3 surfaces? Yes.
No, but it was more like I was asking how can you classify these Turing pairs or degeneration Turing pairs? I assume they are connected.
Okay, so if the moduli space should be connected if you have if you specify the types of the two pieces. But if you specify if you just say, if I'm looking at Turing degenerations of a given K3 surface, there is more than one, but they're definitely, they don't deform into each other in any sense. So for instance, if I look at K3 surfaces of degree 2, which are a fairly simple type, K3 surfaces of degree 2 admit 4 distinct Turing degenerations, and each one forms an 18-dimensional family.
What was this 10 minus d dimensional space that you were mentioning?
Okay, so that's just the moduli. If I'm looking at the moduli space of just the pair XE, so not the full degeneration, just the component.
It's like y compared.
Yeah. So I mean, this is sort of interesting because if you look at moduli of del Pezzo surfaces, it's not extremely well behaved, and especially in some cases you get automorphisms and stuff. Adding in adding in a choice of elliptic curve makes it much better. So you know, if you're looking at, so this has the moduli space of this has connection 10 minus d. I have a conjecture for at least what the open part is like.
This is a curve but maybe with some importance.
Yeah, so for P2, this is going to be just exactly the moduli space of elliptic curves on P2, which is just one-dimensional elliptic curve admits embedding into P2.
So it gets some Newton and complicated scheme structures.
I don't think it does. I mean, I think if we're looking in, if we're in the P2 case, this is just the same as the moduli space of elliptic curves.
This comes from the fact that you get this lattice, so make things rigid.
I mean, it's really, in this situation, because in the P2 case, there's really no lattice, right? I mean, this is just purely, we put the elliptic curve in, and the elliptic curve has enough. The choice of putting the elliptic curve in kills the automorphisms, basically. So we put the elliptic curve in, and all of this terrible stuff disappears. I mean, if we look at, so interestingly, if we look at the elliptic surfaces side, I completely understand the moduli spaces on that side. Because the rational elliptic surfaces, we're then looking at pairs consisting of a rational surface along with a divisor, which is, it's a chain of rational, it's a cycle of rational curves. And those have been widely studied, right? I mean, there's this paper by Gross-Kack and Keel from a couple of years ago, which talks about, so I know what the moduli spaces look like on there. They look very much like moduli spaces of K3 surfaces, in that you've got like a single connected component, and inside there you've got these loci where the lattice polarization jumps, and on the loci where the lattice polarization jumps, you get a stack structure appear. Because you've got choices you've got the usual tier plot behavior.
So the stack structure appears where?
So if you're looking at the rational elliptic curve surfaces, it appears along the loci where the lattice enhances.
So I assume that if you consider all the pairs of these pairs are containing each other, and so you have this.
Yeah. So if you were, I would expect a similar thing for the lattice polarized del Pezzo. So if you're looking at moduli spaces of lattice polarized del Pezzo pairs, then you're going to have some sort of moduli space, but along subloci where the lattice enhances, you're going to start getting. I mean, there's different ways of looking at it, right? You can either say, we're going to look at the moduli space of pairs as I defined it, then you've got the problem of any time you get -2 curves appearing, you get flopping behavior, and that gives you some stack structure. Or alternatively, you say, well, okay, we just contract all the -2 curves which are disjoint from D, and that kills it, and then you just get a nice moduli space.
Okay, I will get ask more questions. Any other questions? So as I said, there are some refractional surfaces